please. Bronzi.
Okay, thank you. So first of all, I'd like to thank the organizers for the opportunity to talk about my work in this great conference. And this is joint work with Roman Schwidtkoi, and it was supported by CNPq, the Brazilian funding. Okay, so we are concerned with the existence and behavior of self-similar solutions for the Euler equations. So here we have the Euler equations, incompressible Euler equations. U is the velocity field, P is the pressure. And as already mentioned during this week, this system is invariant under these transformations here. So if U and P is a solution of system 1, then U lambda and P lambda is also a solution. And we say that U is self-similar if U is equal to U lambda for all lambda. And in this case, U has this special form here. I will call V the self-similar profile. Okay? And one thing you have to note here is that the curl of U, the vorticity, has this scaling here, 1 over capital T minus T, which is consistent with the Biot-Katmai, the blow-up criterion. So if you prove the existence of this type of solution, then we have the formation of singularity in finite time. Okay. Let me just say a few words about this type of problem for the Navier-Stokes. So the first one who raised this question was Leray in his seminal work. So he left this question open. And just to mention here, for the Navier-Stokes equations, alpha has to be equal to 1 because of the scaling of the equation. But then 62 years later, these authors, they proved that in the negative. So there is no self-similar solution under a natural condition. So if U satisfies the energy equality, this condition is very natural. And then this result, these authors gave a simpler proof of the result under a stronger condition. So here you have lock, and they didn't suppose lock. They supposed this stronger condition. And later, Say improved the result. So he supposed a mild assumption, which is U satisfying the local energy estimate. And then again, the solution is only the trivial one. And also, these authors here, they considered a more general notion of self-similar solutions. Namely, they allow a different time function here, more general than this one. But again, no pseudo-self-similar solution. Okay, so let's go back to the Euler equations. And let me say what is the ansatz that we are considering. So suppose U is a regular solution in this time interval here. And suppose also that in a neighborhood of X naught and capital T, the solution has this form. So it is locally self-similar, where the self-similar profile satisfies this system here. So the idea is to understand the behavior of this type of solution, and also if we can prove existence of this type of solution. Well, our motivation is the numerical evidence of self-similar blow-up in 3D. And there is a very recent work on the axisymmetric case, which is not our ansatz here, but I think it's worth to cite this work here because they also did a very careful analysis on the self-similar structure of this of the solution. Okay, so here we have some analytical results. They are very compared with the Navier-Stokes solution, Navier-Stokes case. They are recent, and so he proved the existence of solutions to the self-similar equations on bounded and exterior domains under some hypotheses. And then the other results are on the exclusion side. So they suppose some decay on the solution or some regularity on the self-similar profile, and then the unique solution is the trivial one. And so there is the work of Chai, and this one is on pseudo self-similar solutions, the work of Schombeck. And then Chai and Shivtkoi proved these exclusion results. And in this work here, Shivtkoi also considered the energy measure that I'm going to talk a little bit in the end of the talk. And very, very recently, Chai and Tsai, they considered the ansatz of Hao and Lu of this work here, this numerical work here. And just be careful because this condition here is not the same, it's not compatible with the conditions on Hao and Lu. So this result does not invalidate the result of Hao and Lu. But again, it's an exclusion result also. Okay, let me state the main result of our work. So again, we are considering a regular solution on this time interval 0 to capital T. And suppose that the solution is locally self-similar in this ball. And with this scaling. So this scaling is just because we want this power to be positive. Otherwise, it's just trivially V is equal to 0. And then we suppose that we have a control on the growth of the LP normal shells of the self-similar profile. Okay? So we allow growth here. So this gamma can be positive. Then the conclusion is the following. Either the self-similar profile is identically 0, or we can say something about the behavior of the solution, which is the following. That the L2 norm of V is bounded from above and from below by this quantity here. And this means that the solution, roughly speaking, that the solution carries a positive amount of energy up to the time of blow-up. So I will give just a very brief idea of the proof, and then I will make some comments on the consequences of this result. So the idea of the proof. This bound here is always true because of the conservation of energy and just making a change of variables and using that the vector field U is self-similar, then you can arrive at this inequality here, which is the upper bound. Now, suppose V is not 0, and then suppose by contradiction that the lower bound is not true. Okay, so suppose that there exists a sequence of real numbers Ln such that this quantity here goes to 0 as n goes to 0. But then, using this fact and using the energy inequality for the self-similar variables, we can prove this estimate here. Okay? And then, using an interpolation inequality, using that we have a bound for the L2 norm of V, and using our hypothesis on the LP growth of the self-similar solution, and also we will divide this on shells, then, okay, and then there is a very important part, which is to obtain the estimates on the pressure. So this is the hard work, and I'm not going to show this part, but this is the more important part. But yes, we can obtain, we can derive the right estimates for the pressure. And then, so using these estimates, we plug in this equation, in this inequality here, and then we can improve by delta the decay, or we can decay more or not grow so fast this integral here, and then by a bootstrap procedure, we can arrive at a negative power here, therefore V is equal to 0. Okay. And this is the idea of the proof. Okay, the theorem consequence. So first, in some cases, so for instance, if gamma is less than n minus p alpha, or if it's equal n minus p alpha but has this decay here, then we can prove that, then we obtain that v is equal to 0, because in this case, we can prove that this is not valid. So if this part is not valid, then v is equal to 0. And also, we recover some of the previous exclusion results. And moreover, we have this asymptotic behavior that is this one in the theorem. Okay, so I'm just dividing by the volume here, which is L to the power n. And then we have this. And this is going to play a role in the next slides when we consider the energy measure. Okay, so let me talk just a little bit about the energy measure. So the energy measure is defined as the weak limit of the measures induced by the norm of U squared. Well, the weak star limit is this is the definition of the weak star limit. And we observe that if U is regular at time capital T, then the measure is given by this induced measure. Okay, but if T is a time of blow up, then the good thing is that this energy measure can express how severe the singularity is, or can be. And one way to calculate how severe this singularity can be is through the local fractal dimension of the energy measure. So this is the definition of the local fractal dimension. So the upper fractal local dimension is given by this formula here, and the lower just change it sub by inf. And if these two quantities are equal, then we say that the measure has a fractal local dimension, and is this quantity here. It's defined to be this quantity here. So we measure the measure, and at a point x naught. So the conjecture is the following that we want to analyze. That if the local fractal dimension of the energy measure at the point x naught is equal to d, this is valid if and only if we have this scaling of the L infinity norm of our solution U, the solution of the Euler equations, at a neighborhood of x naught. So the integral of this quantity up to the time of blow up. And then, so our theorem supports this conjecture. So indeed, we observe that, so by the definition of the measure, and using the fact that U has this special form because it's self-similar, and then making this change of variables, we obtain that this measure at this ball is given by this quantity here. But from our theorem, if you remember, this quantity here is less or equal C naught rho L to the power n minus 2 alpha. So we end up here with this rho n minus 2 alpha. Therefore, using the definition of local fractal dimension, we obtain that the dimension of the measure is given by this number here, n minus 2 alpha. But on the other hand, also if U is locally self-similar, then we can compute the L infinite norm. We obtain this quantity here, and then integrating from T to capital T, we obtain that this quantity scales like this. Exactly what we were looking for. And so for the self-similar solutions, we have this, we checked this conjecture. And I don't know if I was too fast. Okay, thank you. Thank you very much for your attention.